All right, so we're looking at vectors, introducing vectors, and Vector the character had it correct when he said it's a mathematical quantity with both a direction and magnitude, and it's represented by an angle. Okay? All right, so now let's make one distinction here.
Wait, isn't it represented by an arrow?
An arrow, yeah. Did I say angle? Oh, sorry. An arrow, okay? Let's make one distinction here between a scalar and a vector, okay? A scalar is simply a quantity or a magnitude, all right, you could say. For example, I could say I'm driving 45 miles an hour, or I lifted up, or I pushed with 100 pounds of force, okay? I could say that we traveled 100 miles, okay? All of those are just scalars. But when I incorporate the concept of direction into it, then I have a vector. It's a magnitude with a direction. So instead of I just drove 45 miles an hour, I was driving 45 miles an hour north on Lyons Road, okay? Or I was pushing to the left with 100 pounds of force. Or we traveled 100 miles southeast, okay? All of those have that idea of direction involved, okay? Now, here we have a couple of things here. When we're talking about velocity, all right, that implies a vector quantity, okay? So there's a magnitude and direction. If you're asked for a velocity, you should give a magnitude and tell what direction it's going, okay? Displacement, that is traveling a certain distance in a certain direction, all right? And force is pounds or newtons if we're in metric in a particular direction. We might be pulling something or pushing something or something like that, okay? Now, I'll warn you here, this lesson, since we're just starting the concept of vectors, we're going to have a lot of notation and a lot of vocabulary. So it's very important that you pick up on all of this notation and vocabulary quickly, all right, as we go through this. So really try to focus today, even though there aren't any real deep concepts, there are a lot of foundational ideas that we need to get settled in our minds before we can move on, all right? So first of all, let's look at the notation. If we're naming a vector, you can name it with a lowercase letter with this little arrow above it, okay? In print, not when you're handwriting, you can use bold font, all right? I don't want you like coloring really hard to try to make it bold. Occasionally, you'll see someone use this notation here with a little tilde above it instead of the arrow above it. That's really uncommon, and frankly, you'll never see me write that. But if you're looking for help online or something and you see that notation, you'll know what they're talking about. It's a vector, okay? So we can name it with a lowercase letter, but we can also name it by a point where it starts and a point where it ends, okay? So a vector from point A to point B would be vector AB like this with the arrow above it, okay? One comment I'll make here, you need to get into your head the fact that just because we're going from a point to a point doesn't mean we're necessarily talking about motion or displacement. That's only one kind. We could be talking about velocities that are impacting it. Like an airplane that's trying to fly one direction and the wind is blowing another direction. Okay? And we'll look at the result of that happening. Or forces. If we have 2 or 3 people all pulling different directions on an object, we have different force vectors, and we would represent them with these things from A to B, but it's not actually dealing with motion, okay? So that's how we would denote a vector in the first place. Then the magnitude of that vector, we use these, they look like absolute value symbols. Sometimes you'll see, or a lot of times you'll see, in order to distinguish from absolute value, they will put the double bars on either side of it, okay? But that's dealing with magnitude. And later on we'll learn how to find magnitude of a vector if it's not given. Okay? So there's some basic notation to start with. So now we have component vectors, okay? There are two ways that you can be given vectors. You could be told the magnitude and direction, like the ones I described earlier. I'm driving 45 miles an hour going north, okay? I specifically told you what the direction and magnitude are. Component vectors don't do that. They instead give a horizontal and vertical component or part of the vector.
So, to make a triangle.
We can use triangles. We're going to use triangles, and that's where the trig comes into play too.
This is literally
Okay.
physics class first trimester. Like,
Good.
Mo and I probably know all of this already.
I don't think you understand. I have this
Alright.
class and then physics after this. So.
Good, good. So this should reinforce what you've learned and hopefully maybe clarify some things, and it'll really, really help you in this class too. Alright, now there's 4 different ways you can write vectors, and I'm going to try to kind of rotate this notation in and use all of them regularly so that you're used to seeing all of these, because the reality is you'll see all of these about equally, you know, out in wherever you're looking at vector stuff, okay? The first kind here, I prefer not to use as much simply because it looks a whole lot like
Coordinates.
coordinates for a point.
But
Okay.
isn't it coordinates for a point at the same time?
If it's a position vector for a point, like the position vector from the origin to a point is just the coordinates of that. We'll see later. But we have those coordinates and we have a vector, same notation. You should be fine unless you have a problem where you're given points and you're dealing with vectors within the same problem. If that's the case, I would avoid using this notation because you're probably going to get mixed up at some point. So that's why we have these 3 other forms as well. We have the parentheses, but notice here we put the horizontal component on top and the vertical on bottom. Do not put a fraction bar. This isn't a fraction. Okay, this is simply an alternative way of writing the vector. Then we have it written kind of like coordinates, but we have these angled brackets. Alright, and then finally here, this is actually what's known as unit vector form. Okay, and it's called unit vector form because I is what's known as the horizontal unit vector, J is the vertical unit vector. We'll talk about unit vectors later this week, but this is just another way that we can denote the same vector. Okay, now what we're talking about here is, let's say we had this vector V that looked like this. Okay? You can see the horizontal component and the vertical component kind of as sides of a right triangle. Okay? So this would be B, and this right here would be A. And you can tell already that we're probably going to be using some right triangle trig and the Pythagorean theorem in here and some other stuff. So, but that's what these components tell us. It's kind of like if you're downtown in a big city and you're asking how to get from one location where you're at to somewhere across town. And obviously, with all the buildings in the way, you can't go in a straight line. Alright, so someone might say, yeah, walk 5 blocks over this way and then 6 blocks up that way and you'll be there. They just gave you a vector in component form to get to where you want to go. Alright? They've just given you directions to get from where you are to where you want to go. The end result is you want to do this, but they told you how to get there horizontally and vertically, okay? Now, let's talk a little bit about magnitude, and really today what we're looking at are vectors that we're drawing. We're going to work later on vectors that are in a more algebraic sense. Here we're looking at them more in a visual sense, okay? So when we're talking about magnitude, we represent that magnitude by the length, okay? Now, I'm not saying that you have to draw everything to scale, but the better you do that, the easier you will find different applications to be. As you work through a problem, you know, if you have a vector whose magnitude is 10 and a vector whose magnitude is 3 and you make them the same length, you're going to confuse yourself.
Yeah.
However, if you have a vector whose magnitude is 10, you know, like this, and a vector whose magnitude is 3 and you make that about that long, then that'll help you understand what's going on in the problem. It'll also, as we look to get angles later on, it'll help you not, you know, to at least make sure your answers make sense based on what it looks like. Okay? We're not going to just go with what it looks like, but it'll help your answers to make sense because you have a general idea because you've drawn it at least somewhat to scale. Okay? Now, when we're talking about magnitude, we're talking about the speed in your velocity vector, or the pounds of force, the distance of your displacement. It's that measurable part, not the direction. Okay? So we have magnitude first. Next we have slope. Okay? As we said already, when you've got this vector, the horizontal and vertical components, A and B, okay, will tell us how to go from one end to the other. But notice here, we can identify this as slope, because the A and B are kind of like what when it comes to slope?
Rise over run.
Yeah, the rise over run. So we could say our slope equals what in this case?
A over B. No, B over A.
You're right.
B over A, okay? B over A. There's another thing noted here, and this is the direction angle. This is something that I don't know if they emphasize as much in physics, but the direction angle, okay, is the angle in standard position that the angle would go, or that the vector would go. So in this case here, we're talking about
North of east.
their angle, yeah, north of east, okay? So there's our angle. Let's say that's our direction angle theta. Okay, how would I find what theta is if all I know are the components of my vector?
SSS.
Hmm,
Wait, if you know SSS, I don't even know.
it's easier than that. Yeah, tangent. We have a right triangle, right? Because horizontal and vertical are perpendicular. So we could use tangent of theta equals our slope, B over A. Okay? So of course theta would be the inverse tangent of B over A. And again, this is another thing we're going to come back to. We're going to actually work on doing some of these, but I'm just kind of introducing everything here in concept at the beginning. Okay, so that's our slope, and along with that, the direction angle of a vector. Okay, next thing we have here are what are known as parallel vectors. Okay, parallel vectors have the same or opposite directions. Okay, now this is kind of odd to think about. You know, you think parallel, they're going the same way. It's actually a little bit more than this, because we could be going the opposite direction, like this one right here, okay, is going the opposite, but it's still parallel. Now, because we're using the inverse tangent to get the direction angle, remember tangent's positive in the first and third quadrants, it's negative in the second and fourth quadrants, that gave us angles where they were opposite of each other. They were exactly 180 degrees apart from each other, okay? That's how we get them parallel here. They have the same or opposite directions. Another thing that we could say is that they have the same slope. Okay? They will have exactly the same slope. They can't have opposite slopes. It would have to be the same slope. So same or opposite direction, or you can think of it as the same slope. And then finally we have this term equivalent vectors. Equivalent vectors have exactly the same direction, exactly the same magnitude. Okay? Same direction and magnitude. And if they have the same direction and magnitude, we would say that all equivalent vectors are also same slope. Therefore they are parallel. Okay? So, all equivalent vectors are parallel. Not all parallel vectors are equivalent though. Okay?
True.
Now let me just illustrate some concepts here. Here we have two guys who are pulling on a box and they have equal strength. Okay? They have an equal amount of strength. They're pulling in the same direction. We would call their two force vectors equivalent vectors. Okay, you can see there they both have vector u. They're the same strength, same direction. Therefore, those vectors are equivalent. Down here, on the other hand, though, now they have a disagreement and they're pulling opposite directions. Okay, we call those opposite vectors. Okay, now opposite vectors, remember, are still parallel. Okay, and they do still have the same magnitude in this case. Opposite vectors always have the same magnitude, they're just opposite directions. So they're parallel but not equivalent. Okay? So parallel but not equivalent. Okay, so that's just sometimes a helpful picture to help us see what's going on here. Okay? Next idea, and this is where we really get into something you got to understand. When we get to the application, the better you understand this right here, the easier those applications will be. Alright? So let's take a quick look, and we're going to slow down for a minute here on vector addition. Okay? Now, if you've done a little with vectors before, you know that with component form, there's an element where we can do vector addition with the components. We'll deal with that in our next lesson, okay? But here I just want to look at it graphically, okay? We have vector u drawn and we have vector v drawn. And if I want to do vector u plus vector v, what we're going to use is what's known as the head to tail method, okay? So, first of all, we start with vector u and we draw that. Okay, so here's our vector u, and then from where we left off with u, we draw vector v. Okay, so here's vector v. So I just did u plus v. Now, you say, okay, well, what's vector u plus v? Is that it, those two pieces? No, vector u plus v is what's known as the resultant vector. This is an important term for you to know really, really well. The resultant vector starts where the first vector started, and it ends where the last vector ended. Okay? And here's the thing, you could add more than just two vectors. We could add 10 vectors together. And it's going to start where the first one started, it's going to end where the 10th one ended.
So it's displacement.
Okay? You look at this just like this, okay? So this would be vector u plus v right here. Okay? Cannon?
So in vector addition, the placement of the vectors does matter.
What do you mean the placement?
Like v plus u would not be the same thing?
Alright, well that's a great question, okay? Cannon's asking, and this really comes to a thing that we have in any realm of mathematics where we're dealing with a different construct. Like we've been dealing with real numbers most of our lives, and then we got these complex numbers thrown in, and there were a couple of rules that were a little bit different. Like for example, multiplication, you had to FOIL. Okay? So there are certain things that were a tad bit different. Now we're dealing with vectors. So the same question kind of holds, you know. For example, what Cannon's really asking here is vector addition commutative? I know that 3 plus 5 equals 5 plus 3, but is vector u plus vector v equal to vector v plus vector u?
No.
Okay? Well, let's look at it geometrically, all right? If I were to do vector v first of all, like this, and then from where I left off, I did vector u.
Yeah, then I guess it is the same thing.
Yeah, it is the same thing. And actually, you know, I said we're using the head to tail method.
When you do the components and you add the x and y, it's going to be the same thing. Right?
It will, yeah. Okay? We're doing the head to tail method. If you were to do both of them like this, some people like to do both of them like this just to make sure they end up in the right spot. This is what's known as the parallelogram method for adding. Okay? Because it forms a parallelogram, and the diagonal is our resultant vector. Okay? So this actually does indicate that vector addition would be commutative. We'll actually prove it when we start doing it with the components. Alright? But you can see here what our result would be. It would be this purple vector right here, u plus v. And that would equal v plus u as well. Okay? So that's our resultant vector. One important thing to do. Think of these vectors when you're doing vector addition as directions if you were driving somewhere. Okay? Because here's what a lot of people do. They say, okay, vector u plus vector v. Here's vector u, and then now I'm going to do vector v. And they do that. Okay? And they have them both starting from the same spot. Okay? That's not going to be vector u plus vector v. Alright? And if you think about it in terms of directions, it'll make sense. If I were telling you, you know, drive north for 1.5 miles, and then drive west for 1/4 mile, and you'll end up at my house. Okay? You wouldn't drive north for 1.5 miles, then come back to school, and then drive west for 1/4 mile. But when you do u plus v like this, that's what you're trying to do. Okay? So think of it as directions, and then it'll make sense. Okay, I'm going to go along u, and then wherever I end up, I'm going to go v next. That'll help you. And that holds true anytime you're dealing with vector addition, even if things are acting on the same object. For example, one place where this can get, people tend to do this is, we'll have an application where an airplane is trying to fly this way, and the wind is blowing like this. And we want the end result. What's actually going to happen to the airplane? Okay? Well, people say, oh, well, the wind is blowing the plane. Here's the plane. It's aimed this way, but the wind's blowing that way. And they do their vector addition wrong. Okay? Instead, you have to think, okay, the plane is doing this, and the wind is doing this, the result will be that. Okay? So again, just the better you understand what we're doing right here, the easier those applications will be later. Okay? Alright, so that's our basic vector addition. the last thing that we have here is scalar multiplication. Now remember, scalar is just a number. It's just a number. But notice if I had 3 times vector u, think back to elementary school when you were learning how to multiply. 3 times something is just that plus itself again, right? So if we did 3u, we have 1u, and then from the end we add another u, and then we add another u. There's a third u. So in the end, 3u is just this really long vector right here. There's 3u. And notice here, when we multiply a vector by a scalar, the direction's not going to change at all. The only thing that changes is the magnitude. So the magnitude would be multiplied by 3, the direction stays the same. Okay? Pretty simple? Okay? All right. Now, I've given you a little bit of practice with these, some on the coordinate plane, all right, with different points and stuff like that. Others where you're just given a vector u and a vector v. But remember, u and v are not bound to a specific location. I could take vector u, I probably should have used this earlier. Okay, let's say that's vector, I don't know why it won't get any shorter. Let's say that's vector v, since it's about the same length. Okay, I can move vector v wherever I feel like. Okay, that's still vector v even though it's moved over somewhere. Okay, so has nothing to do with location. It is simply a vector. Okay. So I've given you a couple of these here with some different combinations of both scalar multiplication and vector addition. Even the opposite vector, that negative, the opposite vector is thrown in there. And then this one is kind of an interesting study here, okay? And they're asking you in this diagram, are these vectors equal? It's a true or false thing. So for example, is C equivalent to S? Well, here's vector C, and here is vector S. Are they the same magnitude? Yeah, they both go over 2 and up 2. Are they the same direction? Yeah. So are they equivalent?
Yes.
Yes. Okay. And like 102, A plus D equals 0. Now that's the 0 vector. That means we have a magnitude of 0, and hence the direction doesn't matter because it's no magnitude. Okay.
Yes. Accuracy.
So, in other words, if we have a 0 vector, we should end up back where we started. If I do A plus D, do I end up back where we started?
Yes.
Yeah, because remember, these are not bound to a location. So A says go up 2 spaces, D says go down 2 spaces. I ended up right back where we started, so that would be true. Okay? Now on the required IP, I gave you the odd ones, so you can try some of these on your own. All right?
Mr. Hickson?
Yes?
What about 103 where it's negative 2 times, like, oh wait, never mind, that's what we did with the other one,
Yeah, double it, and then to make it the opposite. You know, that's kind of how you would have to handle that. All right, so give those a try. We got the required IP, and there's more here that you can try. If you kind of struggled with those and want some more practice, you can do that. Okay?